Now, there's one more thing that we can learn from this force velocity curve that we introduced in the last video, and it has to do with the concept of power. Quite often in sports performance, we're interested in maximizing the power output of a muscle. One way of thinking about power is maximizing power is maximizing the energy output of a muscle. So sprinting, lifting, throwing, all this is based around muscle power. And to get an intuition of how we can go from this force velocity curve to power, I'm going to introduce a few equations that if you've done physics or biomechanics might be familiar to you, but if not, don't worry about it. The actual definition of power is that it's a rate of doing work. So it's some amount of work, say in joules of energy, per unit time. Quite often you'll see the unit of watts of power. So if you do one of those 30-second anaerobic tests on a bike, your power output, your max power output is reported in watts of power, just like a light bulb. So if you're familiar, we can also express work as some force applied over some distance. And if we divide that by amount of time to get power, you'll notice that we get this little distance over time relationship here, which, even if you haven't done physics, you probably know is equal to velocity. So if I go 5 meters in 1 second, I'm moving at 5 meters per second. So this tells us that power is equal to the product of force and velocity. So what that means is that if we're operating at some point on this force velocity curve, we can multiply whatever our force is, which is this amount right here, by whatever our velocity is, which is this amount right here, and the product of those two will give us power. Now notice there's a geometric interpretation to this, which is base times height. So it's like the area of this rectangle, not the area under the curve, but the area of this rectangle specifically, tells us what our current power output is for that muscle. Now, there's a few things to notice about this, and a good way to build intuitions is to start with the extreme cases. So let's start with the extreme case of force is 100%, and remember that's percentage of the maximum isometric force. Force is 100%, but velocity is 0 because that's at this point on the curve, right? So we have 100 times, 0. That's like a rectangle with a height of 100 and a width of 0. Well, the power output there has got to be 0. And then if we just nudge a little bit this way, so maybe like we're at 99%, now we've got a rectangle with a base of like this width and a height of this much. And so the area is going to be really, really, really small, right? Not totally 0, but really small. So that's one way of thinking about an extreme case. And of course, the other extreme case is down here where our velocity is like fully at this max shortening velocity. That's like the fastest speed that the muscle can ever contract at. But of course, if you're at that speed, the force production capability is 0. So that's like a rectangle with this base, but a height of 0. So that's 0 times, we could say like 100% of Vmax, which also equals 0. And again, if you nudge just a little bit up that curve, maybe to here, now you've got like this much force production capability at that velocity. So that area of that rectangle is really small as well. So we can start building intuitions about maybe if we go right here, now we get a bigger area. We go here, we get a really big solid area. If we go here, now we're starting to go back down again. And then of course, if we're down here, then our power output is very close to 0 again. So I'm going to redraw a very similar plot here. In fact, I'm just going to copy the x-axis. This is still muscle shortening velocity, 0 here. Concentric contractions out here with our V max up here, whatever that is, and then eccentric over here. But on the y-axis, I'm going to plot the product of force and velocity, which is power. And we'll drop in those two extreme cases we saw. If your velocity is 0, your power output's got to be 0. And if your velocity is Vmax, your power output is also 0 because you can't produce any force. And you get, if you go at the intermediate points, you get something like this. And it turns out that, of course, what we're interested in is what is the contractile velocity when we maximize power. It turns out that that point is at about 30 to 35% of that maximum shortening velocity. So this has some important implications for training. Suppose you test out maybe different speeds at which you can lift some weight. It turns out that the most powerful motion is going to be the one that's about 30 to 35% of the maximum speed that you can move something at. So if you're interested in optimizing your power output, you want to shoot for that range. And this has some important implications in sports where you have a choice of your we could say velocity or like work or velocity. The best example here is cycling. So in cycling, you have a bicycle with different gears, and you can change the gears of the bike to adjust how fast you have to move your legs, which is proportional to how fast your muscles have to contract. So what cyclists try to do when they're changing gears is they want to get the gear ratio such that they can operate at about 30 to 35% of whatever the fastest speed they could spin their legs at. And it turns out that is what optimizes your power output. So if you've had the experience where you're biking up a hill and you can't go into a low enough gear, that's where you're down here, right? Your velocity is really small, and your power output's really small, even though maybe you're producing a lot of force to try and get up the hill. And if you've had the experience of riding maybe a bike without enough gears, and you're going down a hill, or you're riding really fast and you're already in the highest gear, but you're just spinning your legs around and around and around, you are up here. You're moving too fast and you can't produce enough force to optimize your power output. So in a sport like cycling, this has important implications for what is the appropriate speed at which we should try to find to contract our muscles at if our goal is to optimize or maximize our energy output. Now, there's one more thing that I should talk about because I have the full force velocity curve here, which is what happens over here on the eccentric side. So you might wonder, well, what about if you're up here? What do you still have? Is your power still the product of your force and velocity? So is it this rectangle? And the answer is yes, although with a caveat. Because your velocity is going to be negative here, right, less than 0, when we do this force multiplied by velocity, you're going to get a negative number. And if positive amounts of power have the interpretation of being energy output, then negative power means you are absorbing energy. So a good example of this is maybe landing from a drop jump. Your muscles, say your quads as you land, are working eccentrically. They're lengthening, but they're trying to contract. Now this is it's very advantageous that they can produce a lot of force at that shortening or at that eccentric lengthening velocity. And I actually suspect that this is one of the reasons why muscles adapted to be able to do this, is that it allows you to absorb a tremendously large amount of energy in a small amount of time. That would be having a high magnitude negative muscle power. But in terms of sports performance, because we're usually interested in the power output of muscles, not how much energy can they absorb per unit time, we're generally going to be thinking about the right-hand side of this curve. So this thing. Again, the biggest takeaways: your power output is 0 when you have a muscle velocity of 0, no matter how high the force is. And if the force is, or if you're out beyond the maximum shortening velocity, you can't produce any power at all because you can't produce any force. Finally, muscle power is optimized at about 30 to 35% of the maximum shortening velocity. Maybe I should write that out. Maximum shortening velocity. Which we talked about what that is, this point right here, in the last video. So that is the relationship between the force velocity curve and muscle power output.